So speaking of AlphaFold, so DeepMind's AlphaFold 2 recently was announced to have quote unquote solved protein folding. How exciting is this to you? It seems to be one of the exciting things that have happened in 2020. It's an incredible accomplishment from the looks of it. What part of it is amazing to you? What part would you say is overhyped or maybe misunderstood?
Mhm. It's definitely a very exciting achievement. To give you a little bit of perspective, right? So in bioinformatics, we have several competitions, and so the way you often hear how those competitions have been explained to sort of to non-bioinformaticians is they call it bioinformatics Olympic Games, and there are several disciplines, right? The historically one of the first one was the discipline in predicting the protein structure, predicting the 3D coordinates of the protein. But there are some others. So the predicting protein functions, predicting effects of mutations on protein functions, then predicting protein-protein interactions. So the original one was CASP, or critical assessment of protein structure, and typically what happens during these competitions is experimental scientists solve the structures, but don't put them into the protein data bank, which is the centralized database that contains all the 3D coordinates. Instead, they hold it and release protein sequences. And now the challenge of the community is to predict the 3D structures of these proteins and then use the experimentally solved structures to assess which one is the closest one. Right.
And this competition, by the way, just a bunch of different tangents. And maybe you can also say what is protein folding. And this competition, CASP competition, has become the gold standard, and that's what was used to say that protein folding was solved. Sorry, just to add a little, just a bunch. So if you could, whenever you say stuff, maybe throw in some of the basics for the folks that might be outside of the field. Anyway, sorry.
So the reason it's relevant to our understanding of protein folding is because we've yet to learn how the folding mechanistically works, right? So there are different hypotheses what happens to this fold. For example, there is a hypothesis that the folding happens by also in the modular fashion, right? So that we have protein domains that get folded independently because their structure is stable, and then the whole protein structure gets formed. But within those domains, we also have so-called secondary structure, the small alpha helices, beta sheets. So these are elements that are structurally stable, and so and the question is, when do they get formed? Because some of the secondary structure elements, you have to have a fragment in the beginning and say the fragment in the middle, right? So you cannot potentially start having the full fold from the get-go, right? So it's still it's still a big enigma what happens. We know that it's an extremely efficient and stable process, right?
So there's this long sequence, and the fold happens really quickly.
Exactly.
So that's really weird, right? And it happens like the same way almost every time.
Exactly.
That's
right.
really weird. That's freaking weird.
That's why it's such an amazing thing. But most importantly, right? So it's so when you see the translation process, right? So when you don't have the whole protein translated, right? It's still being translated, getting out from the ribosome. You already see some structural, fragmentation. So folding starts happening before the whole protein gets produced, right? And so this is obviously, one of the biggest questions in modern molecular biologies.
Not like maybe what happens. Like that's bigger than the question of folding. That's the question of like deeper fundamental idea of folding.
Yes,
behind folding.
Exactly. So so obviously, if we are able to predict the end product of protein folding, we are one step closer to understanding sort of the mechanics of the protein folding, because we can then potentially look and start probing what are the critical parts of this process and what are not so critical parts of this process. So we can start decomposing this, so in a way, this protein structure prediction algorithm can be used as a tool, right? So you change the you modify the protein, you get back to this tool, it predicts, okay, it's completely unstable.
Yeah, which aspects of the input will have a big impact on the output.
Exactly. So what happens is, we typically have some sort of incremental advancement. Each stage of this CASP competition, you have groups with incremental advancement, and historically, the top performing groups were, they were not using machine learning. They were using very advanced biophysics combined with bioinformatics, combined with the data mining, and that was that would enable them to obtain protein structures of those proteins that don't have any structurally solved relatives. Because if we have another protein, say the same protein but coming from a different species, we could potentially derive some ideas, and that's so-called homology or comparative modeling, where we'll derive some ideas from the previously known structures, and that would help us tremendously in reconstructing the 3D structure overall. But what happens when we don't have these relatives? This is when it becomes really, really hard, right? So that's so-called de novo de novo protein structure prediction. And in this case, those methods were traditionally very good. But what happened in the last year, the original AlphaFold came into, and all of a sudden, it's much better than everyone else.
This is 2018.
Yeah.
Oh, and the competition is only every 2 years, I think.
And then, so it was sort of kind of a shockwave to the bioinformatics community that we have like a state-of-the-art machine learning system that does structure prediction, and essentially what it does, so if you look at this, it actually predicts the context. So so the process of reconstructing the 3D structure starts by predicting the context between the different parts of the protein, and the context essentially is the parts of the proteins that are in a close proximity to each other.
Right. So it actually, the machine learning part seems to be estimating. You can correct me if I'm wrong here, but it seems to be estimating the distance matrix, which is like the distance between the different parts.
Yeah. So we call it the contact map.
Map.
Right. So once you have the contact map, the reconstruction is becoming more straightforward.
Yeah.
Right. But so the contact map is the key, and so so that what happened, and now we started seeing in this current stage, right, where in the most recent one, we started seeing the emergence of these ideas in others people works, right? But yet here's AlphaFold 2 that again outperforms everyone else. So by introducing yet another wave of the machine learning ideas.
Yeah, there does seem to be also an incorporation. First of all, the paper is not out yet, but there's a bunch of ideas already out. There does seem to be an incorporation of this other thing. I don't know if it's something that you could speak to, which is like the incorporation of like other structures, like evolutionary similar
Yes.
Structures that are used to kind of give you hints.
Yes. So the evolutionary similarity is something that we can detect at different levels, right? So we know, for example, that the structure of proteins is more conserved than the sequence. The sequence could be very different, but the structural shape is actually still very conserved. So that's sort of the intrinsic property that, in a way related to protein folds, to the evolution of the protein of proteins and protein domains, etc. But we know that. I mean, there've been multiple studies, and ideally, if you have structures, you should use that information. However, sometimes we don't have this information. Instead, we have a bunch of sequences. Sequences we have a lot, right? So we have, hundreds, thousands of different organisms sequenced, right? And by taking the same protein but in different organisms and aligning it, so making the corresponding positions aligned, we can actually say a lot about sort of what is conserved in this protein, and therefore, structurally more stable, what is diverse in these proteins. So on top of that, we could provide sort of the information about the sort of the secondary structure of this protein, etc., etc. So this information is extremely useful, and it's already there. So while it's tempting to do a complete ab initio, so you just have a protein sequence and nothing else, the reality is such that we are overwhelmed with this data. So why not use it?
Mm-hmm.
And so I'm looking forward to reading this paper.
It does seem to, like, they've, in the previous version of AlphaFold, they didn't for the evolutionary similarity thing, they didn't use machine learning for that, or they used it as like the input to the entirety of the neural net, like the features derived from the similarity. It seems like there's some kind of quote unquote iterative thing where it seems to be part of the learning process is the incorporation of this evolutionary similarity.
Yeah, I don't think there is a bioarchive paper, right?
There's nothing.
No,
There's
nothing.
nothing.
Yeah,
There's a blog post that's written by a marketing team, essentially.
Yeah.
Which, it has some scientific similarity probably to the actual methodology used, but it's like interpreting scripture. It could be just poetic interpretations of the actual work as opposed to direct connection to the work.
Yeah. So now, speaking about protein folding, right? So in order to answer the question whether or not we have solved this, right?
Yeah.
So we need to go back to the beginning of our conversation, with the realization that an average protein is that typically what the CASP has been focusing on is this competition has been focusing on the single, maybe two domain proteins that are still very compact, and even those ones are extremely challenging to solve, right? But now we talk about an average protein that has 2-3 protein domains. If you look at the proteins that are in charge of the of the process with the neural system, right? Perhaps one of the most recently evolved sort of systems in an organism, right? All of them, well, the majority of them are highly multi-domain proteins. So they are, some of them have 5, 6, 7, and more domains, right? And, we are very far away from understanding how these proteins are folded.
So the complexity of the protein matters here. The complexity of the protein modules or the protein domains. So you're saying solved. So the definition of solved here is particularly the cast competition achieving achieving experimental level performance on these particular sets of proteins that have been used in these competitions.
Well, I mean, I do think that especially with regards to the AlphaFold, it is able to to solve, at the near experimental level, a pretty big majority of the more compact proteins, or protein domains. Because again, in order to understand how the overall protein, multi-domain protein fold, we do need to understand the structure of its individual domains.
I mean, unlike if you look at AlphaZero or like even mu0, if you look at that work, it's nice. Reinforcement learning, self-plane mechanisms are nice because it's all in simulation, so you can learn from just huge amounts. Like, you don't need data. Like, the problem with proteins, like the size, I forget how many 3D structures have been mapped, but the training data is very small, no matter what. It's like millions, maybe 1 or 2 million or something like that. But it's some very small number. But like, it doesn't seem like that's scalable. There has to be, I don't know, it feels like you want to somehow 10x the data or 100x the data somehow.
Yes, but we also can take advantage of homology models, right? So the models that are of very good quality, because they are essentially obtained based on the evolutionary information, right? So you can, there is a potential to enhance this information and use it again to empower the training set. And I think I am actually very optimistic. I think it's been one of these churning events where you have a system that is, a machine learning system that is truly better than the more conventional biophysics based methods.
That's a huge leap.